Close your eyes and imagine the cosmos. When we think of space, we often picture an endless void, cold, dark, and lifeless. A vast emptiness, punctuated by pinpoints of light, stars burning across impossible distances. But this image, while not entirely wrong, tells only half the story. The universe isn't just empty space dotted with stars, it's filled with worlds, countless worlds. Planets orbiting distant suns, each one unique, each one a story waiting to be discovered. We've known for less than a human lifetime that planets exist beyond our solar system. The first confirmed exoplanet orbiting a sun-like star was discovered in 1995, just 30 years ago. In those 3 decades, we've found thousands more. And with each discovery, our understanding of what's possible expands. Tonight, we're going on a journey, not in a physical spacecraft, not yet, but in imagination, guided by real science and actual discoveries. We'll visit worlds so strange they challenge everything we thought we knew about planets. Ocean worlds where water runs thousands of miles deep, lava planets where the surface glows like molten metal, ice worlds drifting alone through the darkness between stars. Some of these worlds might harbor life. Others are so hostile that even our toughest robots would be destroyed in seconds. All of them are real. All of them exist right now, orbiting distant stars, waiting to be explored. Our journey begins with the tools that make these discoveries possible, the telescopes that serve as humanity's eyes in the darkness. Then we'll venture outward, visiting worlds that could be homes for life, worlds covered entirely by alien oceans, and finally, the most extreme and dangerous planets we've ever discovered. The universe is vast, but it's not empty. It's filled with wonders. Let's begin. For most of human history, we could only guess whether planets existed beyond our solar system. We knew our sun had planets, we could see them with our eyes, track them across the night sky. But other stars? They were just points of light, so distant that even through the most powerful telescopes, they remained pinpricks. The problem is one of contrast. Imagine trying to spot a firefly next to a searchlight from 1,000 miles away. That's essentially what astronomers faced when trying to find planets around other stars. The star's light overwhelms everything around it. So astronomers got clever. If you can't see the planet directly, look for its effects. Look for what it does to its star. The first successful method was called radial velocity, or the wobble method. Here's how it works. When a planet orbits a star, it doesn't actually orbit a stationary point. Both star and planet orbit their common center of mass. For a massive planet orbiting close to its star, this creates a detectable wobble in the star's motion. By carefully measuring the spectrum of a star's light over time, astronomers could detect this wobble. A shift toward blue wavelengths meant the star was moving toward us. A shift toward red meant it was moving away. Regular oscillations indicated a planet pulling the star back and forth. In 1995, using this method, Swiss astronomers Michel Mayor and Didier Queloz discovered 51 Pegasi b, the first confirmed exoplanet orbiting a sun-like star. It was a hot Jupiter, a gas giant larger than Jupiter, but orbiting its star closer than Mercury orbits our Sun, completing an orbit in just 4 days. This discovery was revolutionary and also confusing. Hot Jupiters shouldn't exist, according to our theories of planet formation. Gas giants should form far from their stars, where it's cold enough for ice to exist. But here was one baking in its star's heat. This was our first lesson. The universe is more creative than our theories. The transit method revolution. The radial velocity method works, but it's limited. It can detect large planets, especially those close to their stars, but smaller planets, Earth-sized worlds, create wobbles too subtle to measure. Then, astronomers realized they could use another method: transits. When a planet passes between its star and Earth, it blocks a tiny fraction of the star's light. The star dims, just slightly, for a few hours. Then it brightens again as the planet continues its orbit. The amount of dimming tells you the planet's size. The frequency tells you its orbital period. If you're lucky enough to catch multiple transits, you can learn an enormous amount about a distant world without ever seeing it directly. But there's a catch. This method only works if the planet's orbit is perfectly aligned with our line of sight. Most planetary systems aren't oriented this way. To find planets by transits, you need to watch thousands, tens of thousands of stars simultaneously, waiting patiently for those telltale dips in brightness. This requires a specialized instrument, a telescope designed not to take pretty pictures, but to precisely measure the brightness of many stars over long periods. A telescope that can detect a dimming of 1 part in 10,000 equivalent to noticing a single person in a stadium turning off their cell phone. This is exactly what NASA's Kepler Space Telescope was built to do. Kepler's Extraordinary Harvest. Launched in March 2009, Kepler was a relatively simple instrument with an extraordinarily focused mission. It had a 3.1-foot mirror, modest by astronomical standards, but it was equipped with 42 CCD detectors, creating a 95-megapixel camera with a field of view covering about 115 square degrees of sky. That might not sound like much, it's less than 1% of the celestial sphere, but within that small patch of sky in the Cygnus constellation, Kepler could continuously monitor over 150,000 stars. And monitor it did. For 4 years, Kepler stared unblinking at those stars, taking a measurement every 30 minutes. It recorded every flicker, every dimming, building up one of the most complete astronomical datasets ever assembled. The results exceeded all expectations. By the time mechanical failures ended its primary mission in 2013, Kepler had detected over 2,600 confirmed exoplanets, with thousands more candidates awaiting verification. But more important than the numbers was what Kepler taught us about the architecture of planetary systems. Before Kepler, we'd found mostly hot Jupiters and other extreme worlds. They were easiest to detect. But Kepler's patient monitoring revealed something remarkable. Small planets are everywhere. Rocky worlds, super-Earths, mini-Neptunes. Kepler found them by the hundreds. and statistical analysis of its data suggested something profound. On average, every star in our galaxy has at least one planet. With 200 to 400 billion stars in the Milky Way, that means hundreds of billions of worlds. And here's the truly exciting part. Many of those planets orbit in their star's habitable zone, the region where temperatures are right for liquid water to exist on a planet's surface. Kepler's data suggests there could be billions of potentially habitable worlds in our galaxy alone. Billions. Not a handful of rare exceptions, but billions. The universe isn't just full of worlds, it's full of worlds where life might exist. Among Kepler's discoveries was an entire class of planets we'd never imagined. Worlds orbiting in the habitable zones of red dwarf stars. These planets became some of the most promising targets in the search for life beyond Earth. TESS, studying nearby stars. Kepler revolutionized our understanding of how common planets are. But most of the stars it studied were distant hundreds or thousands of light years away, too far for detailed follow-up observations, too faint for spectroscopic analysis of their planets' atmospheres. NASA's Next Planet Hunting Mission, TESS Transiting Exoplanet Survey Satellite, was designed to fill this gap. Launched in April 2018, TESS surveys the entire sky, focusing on the nearest and brightest stars, the ones we can study in detail with other telescopes. TESS doesn't stare at one small patch of sky like Kepler did. Instead, it systematically scans the heavens, observing each section for about a month before moving on. Over 2 years, it images about 85% of the sky, monitoring roughly 200,000 of the brightest stars. The strategy is different, but the goal is the same. Find transiting planets, especially around nearby stars, where we can characterize their properties in detail. And TESS has delivered. Within its first few years of operation, it discovered over 300 confirmed exoplanets, including several potentially Earth-like worlds orbiting in habitable zones. One of TESS's most exciting discoveries came from a small, cool red dwarf star called TOI 700, located just over 100 light-years from Earth. Orbiting this star are 3 planets, one of which, TOI 700d, sits squarely in the habitable zone. This planet is only about 20% larger than Earth. It receives about 86% of the energy Earth gets from the Sun. Computer models suggest its surface temperature could be around 32 degrees Fahrenheit cold, but not impossibly so. With the right atmosphere, liquid water could exist on its surface. TOI 700d completes an orbit every 37 days, compared to Earth's 365. It likely keeps one face toward its star all the time, creating permanent day and night hemispheres. But this doesn't necessarily preclude life. A thick atmosphere could redistribute heat, and organisms are remarkably adaptable. More importantly, TOI 700 is stable. Many red dwarfs are prone to violent flares that could strip away a planet's atmosphere. But observations show TOI 700 is unusually quiet. Over months of monitoring, not a single major flare was detected. This makes TOI 700d one of the most promising targets for the search for life beyond Earth. And because it's relatively close and its star is relatively bright, it's a perfect target for detailed study with next-generation telescopes. The James Webb Space Telescope, a new era. While TESS finds planets, other telescopes study them in detail. And no telescope has revolutionized exoplanet science more than the James Webb Space Telescope. Launched on Christmas Day 2021, Webb is the most powerful space telescope ever built. Its 21-foot mirror, over 6 times larger than Hubble's, collects far more light. And crucially, it observes primarily in infrared wavelengths, where planets shine more brightly relative to their stars. Webb's true power for exoplanet science lies in spectroscopy, analyzing the spectrum of light to determine what a planet's atmosphere contains. When a planet transits its star, some starlight passes through the planet's atmosphere. Different molecules absorb different wavelengths of light, creating a kind of chemical fingerprint. Webb can read these fingerprints. It can detect water vapor, methane, carbon dioxide, and potentially even biosignatures molecules that might indicate the presence of life. In 2023, Webb studied the atmosphere of K218b, a mini-Neptune orbiting in the habitable zone of a red dwarf. The telescope detected both water vapor and methane, and possibly dimethyl sulfide, a molecule that, on Earth, is only produced by life. This isn't proof of life, not remotely, but it demonstrates what's now possible. For the first time in history, we have the technology to not just find potentially habitable planets, but to study their atmospheres, searching for signs of life. This is the beginning of a new era in astronomy, an era where we don't just catalogue worlds, but truly characterize them, where we can ask not just, are there other planets, but are there other living worlds? Part 2. Worlds that could harbour life. Defining the habitable zone. Before we visit potentially habitable worlds, we need to understand what makes a planet habitable. The answer isn't as simple as you might think. The traditional definition focuses on liquid water. Life as we know it requires water. It's the solvent in which biochemistry happens. So, astronomers define a star's habitable zone as the range of distances where a planet's surface temperature would allow liquid water to exist. Too close to the star, and water boils away. Too far, and it freezes solid. The habitable zone is that Goldilocks region in between, not too hot, not too cold. But this simple definition hides enormous complexity. A planet's temperature doesn't depend only on its distance from its star. Atmosphere matters enormously. Venus is closer to the Sun than Earth, but its thick carbon dioxide atmosphere creates a runaway greenhouse effect, raising surface temperatures to 900 degrees Fahrenheit, hot enough to melt lead. Mars is farther from the Sun, and while it has ice, its thin atmosphere and lack of a strong magnetic field mean liquid water can't persist on its surface. Earth itself would be frozen without its greenhouse gases. Our atmosphere traps just enough heat to keep average temperatures above freezing. Without it, our oceans would freeze solid, and Earth would be uninhabitable despite being in the Sun's habitable zone. So when we talk about potentially habitable exoplanets, We're making educated guesses based on limited data. We know a planet's size and orbital distance. Sometimes we know its mass, which tells us about density and composition. Rarely, we can analyze its atmosphere, but we can't see continents and oceans. We can't measure wind patterns or ocean currents. We certainly can't detect life directly, not yet. What we can do is identify worlds with the right basic conditions, the right size, the right temperature, orbiting a stable star. These are worlds worth studying further. Worlds where life is at least possible, and we've found quite a few of them. Proxima Centauri b, our closest neighbor. The nearest potentially habitable exoplanet to Earth orbits the nearest star to our Sun, Proxima Centauri, a small red dwarf just 4.24 light-years away. Proxima Centauri b was discovered in 2016 through the radial velocity method. It's at least 1.3 times Earth's mass, and it orbits in its star's habitable zone, completing one orbit every 11.2 days. 4 light-years might sound far, and it is, by human standards. At the speed of our fastest spacecraft, it would take tens of thousands of years to reach Proxima Centauri b. But in cosmic terms, it's our next-door neighbor, close enough that some scientists have proposed sending tiny, light-sail-propelled probes that could reach it within a human lifetime. But would we want to go there? That depends on what we'd find, and the truth is, we don't know much about conditions on Proxima b. The planet orbits very close to its star, only 0.05 astronomical units, or about 4.6 million miles. At Earth's distance from the Sun, this would be impossibly hot. But Proxima Centauri is a red dwarf, producing only about 0.17% of the Sun's light. At that distance, the planet receives about 65% of the energy Earth gets from the Sun. That's within the habitable zone, but there are complications. First, Proxima Centauri is a red dwarf, and red dwarfs are temperamental. They produce powerful stellar flares that can temporarily increase their brightness by a factor of 10 or more. These flares bathe nearby planets in X-rays and ultraviolet radiation that could strip away atmospheres and sterilize surfaces. Proxima Centauri is known to produce such flares. In March 2016, just months before the planet's discovery was announced, the star underwent a superflare that increased its brightness by a factor of 68 for several seconds. Any life on Proxima b would need to deal with regular radiation bombardment. Second, the planet is almost certainly tidally locked, one face permanently turned toward the star, the other in eternal darkness. The day side would be scorching hot, the night side freezing cold. Only around the terminator, the twilight zone between permanent day and night, might temperatures be moderate. But a thick atmosphere could redistribute heat. Winds would howl from the hot side to the cold side, creating a narrow habitable belt, and life is remarkably adaptable. Even on Earth, organisms thrive in environments we once thought impossible, in boiling hot springs, in frozen Antarctic lakes, deep underground. If Proxima Centauri b has an atmosphere and liquid water, life might find a way, and we might not have to wait long to find out. The planet is close enough and bright enough in its star's light that next-generation telescopes should be able to study its atmosphere, if it has one. Imagine, within our lifetimes, we might know whether the nearest planet to Earth hosts life. What a time to be alive. The TRAPPIST-1 system, 7 Earths around a dim star. In 2017, astronomers announced one of the most remarkable discoveries in the history of exoplanet research. A system of 7 Earth-sized planets orbiting a single star, with 3 firmly in the habitable zone. The star, TRAPPIST-1, is an ultra-cool red dwarf located about 40 light-years from Earth in the constellation Aquarius. It's tiny, only about 9% of the Sun's mass and 12% of the Sun's radius. It's so small and cool that it's barely a star at all. Its surface temperature is only about 4,150 degrees Fahrenheit compared to the Sun's 10,000 degrees. Because TRAPPIST-1 is so dim, its habitable zone is very close to the star. All 7 planets orbit closer than Mercury orbits our Sun. The innermost planet completes an orbit in just 1.5 days. Even the outermost takes only 19 days. Despite this, 3 planets designated TRAPPIST, 1e, 1f, and 1 gram, are in the habitable zone. They're rocky worlds, similar in size to Earth, with surface temperatures that could support liquid water. But the TRAPPIST-1 system is remarkable for more than just having potentially habitable planets. It's remarkable because of how tightly packed it is. The 7 planets are bunched together so closely that if you stood on the surface of one, the others would appear larger in the sky than our moon does from Earth. This proximity creates strong gravitational interactions. The planets tug on each other as they orbit, creating variations in their orbital periods that astronomers can measure. These variations, called transit timing variations, tell us about the planet's masses with remarkable precision. And what we've learned is fascinating. TRAPPIST-1e is almost exactly Earth's size and mass. TRAPPIST-1f is slightly larger. TRAPPIST-1 gram is the largest, about 1.3 times Earth's radius. Their densities suggest they're rocky worlds, but with a twist. Several appear to be less dense than Earth, which could mean they contain significant amounts of water, perhaps 5 to 10% of their total mass. For comparison, water makes up only 0.05% of Earth's mass. If this is correct, these worlds might not be like Earth at all. They might be ocean worlds, with global oceans hundreds of miles deep, underlain by exotic forms of high-pressure ice. TRAPPIST-1e is the most Earth-like of the system. It receives about the same amount of energy from its star as Earth does from the Sun. Computer models suggest it could have a temperate climate with a thin atmosphere, rocky continents, and liquid water oceans. TRAPPIST-1f and 1 gram are colder, but not impossibly so. With the right atmospheric composition, perhaps a thick carbon dioxide atmosphere creating a greenhouse effect, they too could maintain liquid water on their surfaces. The innermost planets are too hot. The outermost is too cold. But the middle 3? They're just right, at least potentially. We don't yet know if these planets have atmospheres, Red dwarfs are notorious for producing radiation that strips away planetary atmospheres, especially for worlds orbiting so close. But TRAPPIST-1 is old, about 7.6 billion years old, nearly twice the age of our solar system. If it were prone to violent flares, they probably would have subsided by now. The James Webb Space Telescope has begun studying these worlds, analyzing starlight filtered through their atmospheres to search for water vapor, carbon dioxide, methane signatures of potentially habitable conditions. Initial observations of TRAPPIST-1b and 1c, the inner planets, suggest they probably lack substantial atmospheres, not surprising given their proximity to the star. But the habitable zone planets await detailed study. Imagine if we find that TRAPPIST-1e has an atmosphere with water vapor and oxygen. Imagine if we detect seasonal variations suggesting active weather patterns. Imagine if we find biosignature gases, molecules that, on Earth, are produced by life. 7 Earth-sized worlds, 3 potentially habitable, orbiting a single star just 40 light-years away. The TRAPPIST-1 system might be the closest thing to a cosmic laboratory for studying Earth-like planets in different conditions. Kepler 452b, Earth's older cousin. Not all potentially habitable planets orbit red dwarfs. In 2015, the Kepler Space Telescope discovered a world orbiting a Sun-like star in the habitable zone, the first such planet ever found. Kepler 452b orbits a G-type star almost identical to our Sun. The star is only slightly larger, brighter, and older. It's about 6 billion years old, compared to the Sun's 4.6 billion. The planet itself is about 60% larger than Earth, making it a super-Earth larger than our planet, but smaller than Neptune. It orbits its star every 385 days, remarkably close to Earth's year, at a distance that's only 5% farther than Earth is from the Sun. This makes Kepler 452b the most Earth-like planet we've found orbiting a Sun-like star. The similarity is striking. If you stood on its surface, you'd see a Sun that looked almost exactly like ours, taking about the same amount of time to cross the sky. But would you want to stand on its surface? That depends on what it's made of. With 60% more diameter than Earth, Kepler 452b could have about 5 times our planet's mass, depending on its composition. If it's rocky like Earth, surface gravity would be about twice what we're used to, challenging, but not impossible for humans to adapt to. But it might not be rocky. At 1.6 times Earth's radius, Kepler 452b sits right at the boundary between super-Earths and mini-Neptunes. It might be a small gas planet with a thick hydrogen-helium atmosphere and no solid surface at all. We don't know. It's too far away, 1,400 light-years, for detailed study with current technology. We can't measure its mass directly, can't analyze its atmosphere, can't determine its composition. What we can do is imagine. If Kepler 452b is rocky, and if it has water and an atmosphere, what would conditions be like? The planet receives only about 10% more energy from its star than Earth does from the Sun. A modest greenhouse effect could keep it comfortably warm. A thicker atmosphere than Earth's would create higher surface pressure, but again, not impossibly so. And here's the truly intriguing part. Kepler 452b has been in the habitable zone for 6 billion years longer than Earth has existed. If life arose there, it's had an extra 1.4 billion years to evolve. On Earth, single-celled life appeared almost as soon as conditions permitted, about 3.8 billion years ago. But complex multicellular life took much longer. It didn't appear until about 600 million years ago. And intelligent life? That took another 500 million years beyond that. If life followed a similar timeline on Kepler 452b, and if the planet truly is habitable, then any life there could be hundreds of millions of years more advanced than us. It's a mind-bending thought. Of course, this is wild speculation based on incomplete data. Kepler 452b might be a lifeless gas planet. It might have suffered a runaway greenhouse effect and become a hellish Venus-like world. Or it might simply be a barren rock with no atmosphere at all. But the fact that we've found even one planet so similar to Earth, orbiting a sun-like star at just the right distance for liquid water, suggests that such worlds are not rare. If one exists in Kepler's small survey area, thousands, millions must exist across the galaxy. Our galaxy likely contains countless Earth-like worlds orbiting sun-like stars, and on at least some of them, conditions must be right for life. Part 3. Ocean worlds and water everywhere. Understanding ocean planets. Water is common in the universe, incredibly common. It's a simple molecule, 2 hydrogen atoms, 1 oxygen atom, and both hydrogen and oxygen rank among the most abundant elements in the cosmos. In the cold outer reaches of planetary systems, water ice is everywhere. Comets are essentially dirty snowballs. Many moons of Jupiter and Saturn are largely made of ice. Even in our asteroid belt, some objects contain significant amounts of frozen water. But we're talking about something different than icy moons. We're talking about ocean planets, worlds where water doesn't just exist, but dominates. Planets where oceans are not just features on the surface, but the defining characteristic. Worlds with water layers hundreds or thousands of miles deep. These aren't science fiction. We've found strong candidates, and theory suggests they should be common. Here's how they form. In the outer reaches of a planetary system where it's cold, planets can grow by accumulating both rock and ice in roughly equal proportions. If such a planet then migrates inward toward its star, and we know this happens frequently, the ice melts, creating a world that's roughly half rock, half water by mass. For perspective, Earth's oceans contain only about 0.02% of our planet's total mass. An ocean planet with 50% water by mass would have oceans over 600 miles deep, deep enough that the bottom layers wouldn't be liquid at all, but exotic forms of high-pressure ice that remain solid even at high temperatures. These deep oceans would be dark, cold, and under crushing pressure. No sunlight could penetrate to such depths, but the ocean wouldn't be lifeless. On Earth, hydrothermal vents on the ocean floor support entire ecosystems that don't depend on sunlight. Heat and chemicals seeping from the planet's interior provide energy for bacteria, which in turn support complex food webs. An ocean planet might host similar ecosystems throughout its deep ocean, sustained by geological activity in the rocky core far below. But would we call this life? Would it count as a living world if life only exists in dark, isolated pockets deep beneath a global ocean, completely cut off from the surface? That's a philosophical question. But scientifically, what's exciting is that ocean planets seem to be common, and they expand the possible habitats for life far beyond traditional Earth-like worlds. GJ 1214b, the first ocean planet candidate. The first strong candidate for an ocean planet was discovered in 2009, orbiting a small red dwarf star called GJ 1214, about 48 light-years from Earth. GJ 1214b is about 2.6 times Earth's radius and roughly 6.5 times Earth's mass. Those numbers are important. They tell us the planet's average density is only about 1.9 grams per cubic centimeter, much less than Earth's 5.5 grams per cubic centimeter. This low density means the planet can't be pure rock. If it were solid iron and rock like Earth, it would be much denser. The planet must contain large amounts of lighter material, and the most likely candidate is water. Calculations suggest GJ 1214b might be about 75% water by mass, with a rocky core making up the remaining 25%. This would give it an ocean over 600 miles deep. But this wouldn't be like Earth's oceans. On Earth, the ocean floor is at most 7 miles down, and the pressure there is about 1,000 times atmospheric pressure. On GJ 1214b, the bottom of the liquid ocean might be 600 miles down, where pressure reaches millions of atmospheres. At such pressures, water behaves strangely. Below a certain depth, it doesn't remain liquid no matter how hot it gets. Instead, it transforms into exotic forms of hot ice, crystalline structures denser than liquid water, remaining solid at temperatures of hundreds of degrees. So GJ 1214b might have this structure. At the bottom, a rocky core about the size of Earth. Surrounding that, a layer of hot, high-pressure ice, several hundred miles thick. Above that, a liquid ocean layer a few hundred miles thick. And above that, a thick, steamy atmosphere transitioning gradually from gas to liquid with no clear surface. The planet orbits extremely close to its star, only about 1.3 million miles, completing an orbit every 38 hours. Despite the star's dimness, this makes GJ 1214b hot. Surface temperatures might range from 400 to 550 degrees Fahrenheit, depending on the atmosphere's reflectivity. At these temperatures, the ocean would be perpetually boiling. The boundary between ocean and atmosphere would be blurred, a gradual transition from steam to liquid water as you descend. Life in such an environment seems unlikely, but not impossible. Even at boiling temperatures, life exists on Earth. Thermophilic bacteria thrive in hot springs at 200+ degrees Fahrenheit. In the crushing pressures and total darkness of GJ 1214b's deep ocean, similar extremophiles might find a niche. But honestly, the conditions seem marginal for life. What makes GJ 1214b exciting isn't that it might be inhabited, it's that it represents an entirely new class of worlds we never predicted. We thought planets came in two types: rocky terrestrial worlds like Earth and gas giants like Jupiter. But GJ 1214b is neither. It's something else entirely, a water world, with more ocean than our minds can easily comprehend. And if one exists relatively nearby, many more must exist throughout the galaxy. K218b, a temperate ocean world with tantalizing hints. In 2023, the James Webb Space Telescope turned its attention to K218b, a mini-Neptune orbiting a red dwarf star 124 light-years away. What Webb found made headlines around the world. K218b is about 8.6 times Earth's mass and 2.6 times Earth's radius, similar to GJ 1214b. It orbits in its star's habitable zone, receiving about the same amount of energy Earth gets from the Sun. Webb analyzed the planet's atmosphere by studying starlight filtering through it during a transit, and it found something remarkable: clear signatures of both water vapor and methane in the planet's atmosphere. That alone was exciting direct evidence of water on a potentially habitable world. But Webb found something else too: possible evidence of dimethyl sulfide, or DMS. This is where things get interesting. DMS is a molecule that, on Earth, is only produced by life. Specifically, by marine phytoplankton, microscopic organisms in the ocean that produce DMS as a metabolic byproduct. Does this mean we've found life on K218b? No, absolutely not. The DMS detection is preliminary and needs confirmation. And even if confirmed, DMS could potentially be produced by non-biological processes we don't yet understand. But it's tantalizing. Webb has detected methane and water vapor on a potentially habitable ocean world molecules that could support life, and possibly a molecule that, on Earth, is a biosignature. The James Webb Space Telescope's observations suggest K218b might not be a thick atmosphere mini-Neptune at all, but rather a Hycean world, a new hypothetical class of planets with liquid water oceans beneath hydrogen-rich atmospheres. Hycean worlds are an exciting concept. They're planets larger than Earth, but smaller than Neptune, with thick hydrogen atmospheres and potentially habitable ocean surfaces underneath. The hydrogen atmosphere would create a strong greenhouse effect, keeping the ocean warm even far from the star. Such worlds could be much more common than Earth-like planets. They can exist farther from their stars in a wider habitable zone, and their larger size means they're easier to detect and study. K218b might be our first confirmed Hycean world. If so, it opens up an entirely new category of potentially habitable planets. Follow-up observations are planned. Webb will study K218b's atmosphere in more detail, looking for additional biosignatures: oxygen, ozone, phosphine. Other telescopes will search for similar worlds. Within a decade, we might know whether K218b truly shows signs of life. And even if it doesn't, We've learned that ocean worlds exist in habitable zones with temperatures that could support life. The universe of possibly inhabited worlds just got a lot larger. Enceladus and Europa, ocean worlds in our backyard. We don't need to look light years away to find ocean worlds. 2 moons in our own solar system, Saturn's Enceladus and Jupiter's Europa, almost certainly harbor vast liquid water oceans beneath icy shells. These aren't exoplanets, but they're relevant to our story because they show us what ocean worlds can be like. And they might be our best chance of finding life beyond Earth within our lifetimes. Europa, Jupiter's 4th largest moon, is covered in a shell of water ice, but this shell isn't static, it's cracked and fractured, with huge ice plates that have shifted and rotated. Some regions show features that look like icebergs frozen in place. All this evidence suggests that beneath the ice lies a global ocean of liquid water, kept warm by tidal heating. As Europa orbits Jupiter, the giant planet's gravity stretches and squeezes the moon, generating internal friction that produces heat. Scientists estimate Europa's ocean might be 40 to 100 miles deep, more water than all of Earth's oceans combined. And where there's liquid water and energy, there could be life. Enceladus is smaller than Europa, but it's even more exciting in some ways. We know it has a subsurface ocean because we've seen the evidence directly. Geysers erupting from its south polar region, spraying water ice and organic molecules into space. NASA's Cassini spacecraft flew through these geysers multiple times, analyzing their composition. It found water ice, salt, silica particles, and organic molecules including methane. The presence of silica suggests hydrothermal activity on the ocean floor, similar to what we see at Earth's deep ocean hydrothermal vents. These hydrothermal vents are crucial. On Earth, they're oases of life in the deep ocean. Superheated water, rich in minerals and chemicals, provides energy for bacteria that form the base of complex food chains. Tube worms, crabs, fish, entire ecosystems thrive in the darkness, independent of sunlight. If Enceladus has active hydrothermal vents beneath its ice, it has all the ingredients for life: liquid water, energy, and organic molecules. The same might be true for Europa. NASA is planning missions to both worlds. The Europa Clipper, scheduled to launch in 2024, will make dozens of flybys of Europa, studying its ice shell and searching for plumes of water vapor. It will map the moon's surface in unprecedented detail and analyze the composition of any material ejected from the subsurface ocean. A mission to Enceladus is also being discussed. A spacecraft could sample the plumes directly, analyzing them for complex organic molecules or even microbial life itself. We wouldn't need to land or drill through miles of ice. The moon is obligingly spraying its ocean into space for us to study. Within the next few decades, we might know whether life exists in the oceans of Europa or Enceladus. And if it does, that would be profound. It would mean life arose independently at least twice in our solar system, and if it happened twice here, it must have happened countless times across the universe. Ocean worlds, whether icy moons in our own solar system or water-rich exoplanets orbiting distant stars might be the most common habitats for life in the galaxy. Not Earth-like worlds with continents and shallow seas, but alien oceans hidden beneath ice or wrapped in thick atmospheres. The search for life might lead us not to worlds that look like Earth, but to worlds utterly unlike anything we imagined. Part 4. Infernal Worlds and Extreme Planets. When worlds go wrong, not all planets are potentially habitable. In fact, most aren't. The universe is filled with worlds so hostile, so extreme, that they challenge our understanding of what a planet can be. Some orbit so close to their stars that their surfaces are molten. Others have been ejected from their solar systems entirely, drifting alone through interstellar space. There are planets where it rains glass sideways in supersonic winds, worlds with atmospheres of vaporized rock, planets being slowly devoured by their dying stars. These worlds won't host life, at least not life as we know it, but they're fascinating in their own right. They show us the full range of planetary possibilities, from the merely habitable to the absolutely apocalyptic. They also teach us about planetary evolution. Earth is temperate now, but in its early history, it was a hellish world of molten rock and toxic atmosphere. Venus, Earth's twin in size and composition, suffered a runaway greenhouse effect that transformed it into an inferno. Mars once had liquid water on its surface, but lost its atmosphere and became a frozen desert. The extreme exoplanets we've discovered aren't just curiosities, they're laboratories for understanding how planets live and die, how they form, migrate, evolve, and sometimes destroy themselves. Let's visit the most extreme worlds we've found, planets at the very edges of possibility. Hot Jupiters, giants too close to home. The first exoplanet ever discovered around a sun-like star, 51 Pegasi b, was shocking because it shouldn't exist, at least not where it was found. 51 Pegasi b is a gas giant similar in size to Jupiter. But while Jupiter orbits the Sun at a distance of 480 million miles, taking nearly 12 years to complete one orbit, 51 Pegasi b orbits its star at only about 4.8 million miles, less than 1/8 Mercury's distance from our Sun. It completes an orbit in just 4.2 days. At that distance from a Sun-like star, temperatures reach 1,800 degrees Fahrenheit. The planet's atmosphere is being continuously blasted by intense radiation. The day side is scorching hot, the night side slightly cooler, creating massive atmospheric flows, winds that scream around the planet at thousands of miles per hour. This is what astronomers call a hot Jupiter, and after that first discovery, we found hundreds more. They're everywhere. About 1 in every 100 sun-like stars has a hot Jupiter. But according to our theories of planet formation, they shouldn't exist at all. Gas giants can only form far from their stars, where it's cold enough for ice to condense. The ice becomes the core around which gas accumulates, eventually creating a massive planet like Jupiter or Saturn. So how do hot Jupiters get so close to their stars? The answer is migration. They form far out in their solar systems, then spiral inward over millions of years. Gravitational interactions with the disk of gas and dust from which they formed, or with other planets, can cause their orbits to decay, bringing them closer and closer to their stars. Some hot Jupiters are still migrating inward. Eventually, they'll migrate too close. The star's gravity will tear them apart, creating a brief but spectacular display as the planet's atmosphere is stripped away and consumed by its parent star. HD 189733b is one of the best studied hot Jupiters. It's slightly larger than Jupiter, orbiting its star every 2.2 days at a distance of only 2.9 million miles. Temperatures on the day side reach 1,700 degrees Fahrenheit. But temperature isn't HD 189733b's most extreme feature. The planet's atmosphere contains clouds of silicate particles, essentially tiny shards of glass. And the planet's intense heat drives winds up to 5,400 miles per hour, 7 times the speed of sound. Imagine, it literally rains glass sideways on HD 189733b. Glass particles form in the cooler upper atmosphere, then fall as the atmosphere circulates, accelerated by supersonic winds until they're moving fast enough to sandblast anything in their path. The planet also appears deep blue when observed in visible light, a beautiful cobalt color reminiscent of Earth. But this isn't caused by oceans. It's caused by the scattering of light by those same glass particles in the atmosphere. It's a beautiful world from a distance. Up close, it's hell. WASP 12b, a planet being devoured. Hot Jupiters are extreme, but some are more extreme than others. And WASP 12b might be the most extreme of all. This planet orbits its star at only 2.1 million miles, so close that it completes an orbit in just 1.1 days. At this distance, the star's gravity creates enormous tidal forces that are literally tearing the planet apart. The planet is stretched into an egg shape, elongated by tidal forces, and it's losing mass. About 189 quadrillion tons of material per year is being stripped from the planet's atmosphere by the star's intense radiation and gravity. This material forms a diffuse disk around the star, gradually spiraling inward to be consumed. The planet is feeding its star, and in the process, destroying itself. Astronomers estimate that WASP 12b has only about 10 million years left before it's completely consumed. That might sound like a long time, but in astronomical terms, it's nothing. The planet is in its death throes, and we're fortunate in a morbid sort of way to be observing it at this particular moment in its history. The planet's day side is incredibly hot, about 4,600 degrees Fahrenheit, hot enough to vaporize iron. At these temperatures, molecules break apart. Even water and carbon dioxide can't exist as molecules, they're torn into individual atoms by the heat. Spectroscopic observations have detected vaporized metals in the planet's atmosphere, including magnesium and iron. The atmosphere itself is likely a hot haze of atomic hydrogen and helium, with clouds of vaporized rock condensing in cooler regions before being ripped apart again by the heat. WASP 12b is sometimes called the Black Planet because it's one of the darkest exoplanets ever discovered. It reflects less than 6% of the light that hits it, making it blacker than asphalt. The planet absorbs almost all the starlight that reaches it, which only makes it hotter, which only accelerates its destruction. Within 10 million years, WASP-12b will be gone, completely consumed by its star. But new hot Jupiters will form, migrate inward, and meet the same fate. This is the ultimate destiny of any planet that ventures too close to its parent star. Coro T7b, the lava planet. Hot Jupiters are gas giants, but extreme heat isn't limited to large planets. Coro T7b, discovered in 2009, was one of the first rocky exoplanets ever found, and it's possibly the most hellish world we've discovered. Coro T7b is only about 1.7 times Earth's radius and 4.8 times Earth's mass, making it a super-Earth in size but anything but Earth-like in conditions. It orbits its star at a distance of only 1.6 million miles, completing one orbit every 20 hours. At this distance, the star's gravity has tidally locked the planet. One side permanently faces the star in eternal day. The other side faces away into eternal night, and the temperature difference is extreme. On the day side, temperatures reach 4,200 degrees Fahrenheit, hot enough to vaporize rock. The planet likely has a lava ocean on its day side, with waves of molten silicate rock crashing against shores of partially solidified magma. But it gets stranger. At these temperatures, rock doesn't just melt, it boils. The planet probably has an atmosphere, but not one made of gases we'd recognize. Instead, the atmosphere is made of vaporized rock. Clouds of silicate vapor hang over the lava ocean, occasionally precipitating as rain of liquid rock. On the night side, temperatures plummet to about -220 degrees Fahrenheit. It's cold enough that any atmosphere would freeze solid and fall to the surface as snow made of rocks. The planet might have a thin shell of solid rock on the night side, while the day side remains molten. Between the day and night sides, around the terminator, conditions are less extreme but still hostile. This is where the vaporized rock condenses and falls as liquid, creating rivers of lava flowing from the hot side toward the cold side. The temperature gradient drives fierce winds. Atmosphere superheated on the day side rises and flows toward the night side, where it cools, solidifies, and falls. Then, surface flows carry the solidified material back toward the day side, where it's heated again and vaporizes, completing the cycle. It's like a planet-wide lava lamp, but the lava is vaporized rock and the liquid is molten magma. Nothing we've experienced on Earth prepares us for conditions on Coro T7b. It's a planet from a nightmare, where the ground itself boils away during the day and snows back down at night. HD 209458b, the evaporating planet. Some planets aren't just hot, they're disappearing. HD 209458b, nicknamed Osiris, was one of the first exoplanets ever discovered by the transit method, and it revealed something unexpected. The planet is evaporating. HD 209458b is a hot Jupiter orbiting its star every 3.5 days at a distance of about 4.3 million miles. Temperatures on the day side reach about 1,800 degrees Fahrenheit hot, but not as extreme as some worlds we've discussed. But the planet is particularly vulnerable because of its low density. It's a puffy hot Jupiter with less than half the density of Jupiter despite being similar in mass. This means its atmosphere extends far from the planet's core, making it easier for stellar radiation to strip away atmospheric gases. In 2003, astronomers detected a huge cloud of hydrogen surrounding HD 209458b, extending out over 120,000 miles from the planet, nearly half the distance to its star. The cloud is shaped like a comet's tail, with material streaming away from the planet as stellar winds blow it into space. The planet is losing about 100 million tons of hydrogen per year. At that rate, it will lose only a small fraction of its total mass over the remaining lifetime of its star. But other elements are escaping too. Oxygen, carbon, and nitrogen have all been detected in the escaping atmosphere. What's happening is atmospheric escape driven by extreme ultraviolet radiation from the star. The radiation heats the upper atmosphere to temperatures of over 18,000 degrees Fahrenheit, hot enough that hydrogen atoms move fast enough to escape the planet's gravity. Heavier elements normally couldn't escape, they're bound too tightly by gravity. But the escaping hydrogen acts like a drag, pulling the heavier elements along with it. It's like a river carrying away soil. The water provides the energy to move material that couldn't flow on its own. HD 209458b is slowly bleeding away its atmosphere. Eventually, billions of years from now, it might be reduced to a bare core, a Neptune-sized world stripped down to just rock and ice, its gaseous envelope completely gone. This process might be common. Many hot Jupiters might have started as even larger planets before stellar radiation stripped away significant portions of their atmospheres. And smaller planets orbiting close to their stars might be completely destroyed, evaporated down to nothing. Rogue planets, worlds without stars. All the planets we've discussed orbit stars, but not all planets do. Some wander alone through the darkness of interstellar space, orphaned worlds ejected from their home solar systems. These are called rogue planets or free-floating planets, and they're surprisingly common. Gravitational simulations suggest there might be billions of them in our galaxy, possibly more rogue planets than stars. How do they form? Most are likely ejected from planetary systems during chaotic early periods, when planets are still migrating and interacting. A close encounter between two planets can result in one being flung into a highly elliptical orbit or even ejected from the system entirely. Some rogue planets might form like stars do, from the direct collapse of clouds of gas and dust. These would technically be sub-brown dwarfs rather than planets, but the distinction is blurry. An object with planetary mass that never orbited a star is effectively a rogue planet regardless of how it formed. Detecting rogue planets is incredibly difficult. They emit no light of their own except faint infrared radiation from their cooling surfaces. They're visible only if they pass directly in front of a background star, temporarily magnifying its light through a process called gravitational microlensing. Surveys using microlensing have detected several candidate rogue planets, and statistics suggest Jupiter mass rogues might be twice as common as main sequence stars. Smaller Earth mass rogues could be even more common. There might be trillions of them wandering our galaxy. But could a rogue planet support life? At first, this seems impossible. Without a star, there's no external source of heat or light. Any world ejected from its solar system would quickly freeze solid as it drifted into interstellar space. But not necessarily. A massive planet with a thick hydrogen atmosphere could retain heat from its formation for billions of years. Radioactive decay in the core would provide additional warmth. If such a planet had a subsurface ocean like Europa or Enceladus, that ocean might remain liquid even in interstellar space, heated by tidal forces if the planet had large moons or by radioactive decay. Such a world would be utterly dark, no stars, no sun, just eternal night. But life doesn't require light. Deep ocean ecosystems on Earth prove that. A rogue planet with a subsurface ocean could potentially support life around hydrothermal vents, completely independent of any star. We might never know if life exists on rogue planets. They're too difficult to study in detail. But the mere fact that they exist expands our understanding of where life might emerge. Not just on planets orbiting stars, but on worlds wandering the darkness between stars, carrying their own heat and water through the void. PSRB 1257 plus 12, planets of a dead star. Some of the strangest exoplanets ever discovered don't orbit living stars, they orbit dead ones. PSRB 1257 plus 12 is a pulsar, the rapidly rotating remnant of a star that exploded as a supernova. The core collapsed into a sphere only about 12 miles across, but containing more mass than our Sun, rotating 161 times per second and emitting beams of radiation like a cosmic lighthouse. In 1992, astronomers discovered that this pulsar had planets, 3 of them. This was actually before the first exoplanet around a sun-like star was discovered. These pulsar planets were the first confirmed worlds beyond our solar system. Their existence is baffling. The supernova that created the pulsar should have destroyed any planets in the original system. Temperatures would have reached millions of degrees. The shock wave would have vaporized solid rock. Any planets that existed should have been blown away entirely. Yet these planets exist. They're small too, a roughly Earth mass. One is much smaller. They orbit at distances of 0.19, 0.36, and 0.46 astronomical units, comparable to Mercury's distance from our Sun. There are 2 possibilities. Either these planets survived the supernova somehow, shielded perhaps by being on the far side of the star when it exploded, or they formed afterward from the debris disk left behind by the explosion. If they formed after the supernova, they're second-generation planets, born from the ashes of destroyed worlds. If they survive the supernova, They're the toughest planets we've ever found, worlds that endured the most violent event in the universe, short of a gamma-ray burst. Either way, they're hellish worlds. The pulsar bathes them in intense radiation, not just visible light, but X-rays, gamma rays, and particle radiation. Any atmosphere would be stripped away almost instantly. The surface would be continuously bombarded by radiation energetic enough to trigger nuclear reactions. And the pulsar itself is gradually spinning down as it loses energy. Eventually, billions of years from now, it will stop emitting its beams. The planets will drift in darkness, orbiting a dead cinder no longer generating any radiation. These are worlds at the absolute end of a solar system's life cycle, planets that outlived their star, now orbiting its corpse in a system slowly winding down to eternal silence. Conclusion: the grand diversity of worlds. We've traveled far tonight, from the telescopes that serve as humanity's eyes in the cosmos, to potentially habitable worlds where life might exist, to ocean planets with seas hundreds of miles deep, and finally to the most extreme and hostile planets ever discovered. What have we learned? Perhaps most importantly, that the universe is far more creative than we ever imagined. Before 1995, we had one template for planetary systems, our solar system, with small rocky worlds close to the sun and gas giants farther out. We thought this was how all planetary systems must be arranged. We were wrong. The universe has given us hot Jupiters orbiting closer than Mercury, super-Earths that don't exist in our solar system at all, ocean worlds where water dominates, rogue planets wandering alone through interstellar space, planets orbiting dead stars, worlds where it rains glass, where rocks vaporize, where surfaces are liquid lava, and habitable worlds, so many potentially habitable worlds. Billions across our galaxy alone, orbiting red dwarfs and sun-like stars, ranging from rocky Earth-like planets to ocean worlds unlike anything we imagined. The question is no longer, are there other worlds? The answer is overwhelmingly yes, hundreds of billions of them in our galaxy alone, and trillions more in other galaxies. The question is now, what are these worlds like, and do they host life? We're beginning to answer these questions. The James Webb Space Telescope can now analyze the atmospheres of distant planets, searching for the chemical signatures of life. Future telescopes will be even more powerful, capable of directly imaging Earth-like planets and studying them in detail. Within our lifetimes, we might detect biosignatures on an exoplanet, oxygen and methane in the same atmosphere, or other molecules that suggest biological activity. We might discover microbial life in the oceans of Europa or Enceladus. We might even make contact with intelligent life beyond Earth. Or we might find that life is rare, that Earth is an exception, that the universe is filled with worlds but empty of living things. That would be profound too. It would make our existence even more precious, knowing we're alone or nearly so in the cosmos. But I don't think we're alone. The sheer number of worlds, the diversity of environments, the fact that life arose on Earth so quickly after conditions permitted all of this, suggests life should be common. Not necessarily intelligent life, but life in some form. bacteria, archaea, simple organisms clinging to existence in hostile environments or thriving in temperate ones. The universe is vast beyond comprehension, 93 billion light-years across in the observable portion alone, containing hundreds of billions of galaxies, each with hundreds of billions of stars, most with planets of their own, trillions upon trillions of worlds. And we've barely begun to explore them. We've found a few thousand exoplanets, studied a few dozen in detail. We've scratched the surface of cosmic reality, but we've learned enough to know this. The universe is filled with wonders. From potentially habitable ocean worlds to hellish lava planets, from worlds orbiting binary stars to rogue planets drifting through darkness, from super-Earths to mini-Neptunes to giants larger than Jupiter, the diversity is staggering. Every star is a sun to its own planets. Every planet is a world, complete with its own geology, weather, and history. Some might have life. All are worth studying. The ancient Greeks believed the stars were fixed lights embedded in crystal spheres. For most of history, we didn't know planets existed beyond our solar system. It's been less than 30 years since we confirmed the first one. In that short time, we've revolutionized our understanding of planetary science and our place in the cosmos. We've learned we're citizens not just of Earth, not just of a solar system, but of a galaxy filled with worlds beyond counting. The journey has just begun. The next few decades will bring discoveries we can't yet imagine, new types of planets, new insights into how worlds form and evolve, perhaps even the discovery of life beyond Earth. The universe of worlds awaits, and humanity, for the first time in its history, has the tools to explore it. So look up at the night sky. See those stars? Each one is probably orbited by planets, worlds as diverse as imagination allows, and more. Some might be homes to life, looking up at their own skies, wondering if they're alone. They're not. We're here. And soon, perhaps, we'll find each other among the stars, fellow travelers in this vast cosmic ocean, separated by distance but connected by the simple fact that we exist. We wonder, and we look up at the night and dream of other worlds. The universe is vast, but it's not empty. It's filled with worlds, countless worlds, each one unique, each one a story. And we've only just begun to read them.